has a very long career and a very important one in optimization. He's one of the leading researchers in this area in Russia. And he will talk about the convexity principle and its applications in linear algebra, optimization, and control. Boris.
So convexity plays a key role in many fields. And for instance, today I was very much surprised to learn that it also works in linguistics. But I'll have in mind mainly such traditional applications as optimization and control. And as you know, in control, in optimization, convex problems have very nice properties. Local minima coincides with global one. Necessary optimality conditions coincide with sufficient ones. There are no problems in construction of effective minimization methods. We have very nice duality theory and so on. So actually, convexity is very attractive thing, and well, it can be seen, but unfortunately, it is just a small island. A small island in the ocean of non-convexity. So it's really important to find some other situations where a problem looks like non-convex, but it shares some convexity properties. And my talk will be about one result in this direction. So let me start with this theorem. So let's consider two Hilbert spaces and a map from X to Y. And we assume that this map is C11, and L is a Lipschitz condition, a Lipschitz constant for a derivative. So the only strong assumption is, well, we have some distinguished point A in the space X. So this point A is assumed to be regular. That is, the linear operator, the derivative at this point, maps X onto Y. That's a surjection. So then it's well known that there exists some positive constant nu that this condition holds, where star denotes conjugate operator. Okay, so that's all. And under these assumptions, the following simple theorem holds, the following result holds. So if we take some ball centered at this point A, and if the radius of this ball, epsilon, is small enough, then the map, the image of this ball under the map F is convex. That is, the set of all points which are images of points in this ball is a convex set. So we have our ball of the radius epsilon. We have this nonlinear map, and we have this image F capital. So the first glance, the result looks to be strange a little bit. Well, we have a nonlinear map, so why the image should be convex? But nevertheless, this is true. And I'll try to explain you why it's the case. First of all, it's important that we deal in Hilbert space, not in a Banach space. So a ball in this space, it is a strongly convex set. So I remind what is a strongly convex set. So if we have 2 points in a set, then not only half sum of these points is in the set, it's the definition of convexity, but also some ball with radius which is proportional to square of distance between these points times some constant, the entire ball is inside the set. So this property for Hilbert space can be verified very simply. It's just follows from parallelogram equality. Okay, so we have this property. The second thing which works here, well, so how can we prove the theorem? We take 2 points in our ball. We look at their maps. Then we take the center of this interval and look at its map. And of course, it is, well, somewhere in this set F capital. But now we look at the center of image, and we are to prove that there exists some point y such that its image is exactly this center. So to validate this, we should use some theorem on solvability of nonlinear equations. And actually, we have such theorems. The first one was the famous theorem of Graves of 1950 on nonlinear mappings. But actually, I need a little bit more precise one, which I proved many years ago. And this theorem not only gives the solvability condition, but it also has gives some bounds for the solution. Okay, so with these 2 results in mind, we can easily prove the theorem. Okay, so let's discuss what we have. So first of all, as I said, it is important that we consider Hilbert space. If we deal with Banach space, then a ball there can be, say, something like this, a cube, and its image, could be, well, something, assume that this derivative is close to identity, but not quite precisely identity. So the image could look like something like this. So it loses convexity under small perturbation. And actually, well, this drawing explains why the theorem is true. Because, well, we have a strongly convex set. Then if we had a linear map, then its image will be an ellipsoid. An ellipsoid, a non-degenerate ellipsoid. So it's again strongly convex set. And our map, nonlinear map, is close to this linear one. So this ellipsoid cannot lose convexity under small perturbations. So it is why the theorem holds. But what is interesting and what is still open, so as I said, it is definitely not true, the result is definitely not true for spaces like L1 or L infinity, or finite dimensional spaces of this sort. But what happens in uniformly, is it true for uniformly convex Banach spaces? It's an open question. Okay, the second command that actually it was not important that we deal with a ball. This original set was a ball. What is really, the only thing which is important was this strong convexity principle, assumption. So it can be replaced, ball can be replaced with any other strongly convex set. Well, then we can establish some additional properties of this image. For instance, it's not only a convex set, but it's strictly convex set. It has a non-empty interior, and interior is generated by interior of a ball, and the boundary is the image of the sphere, of the boundary points of the ball. And last command, that smoothness assumption that the function is C11, it is important. Some people try to construct counterexamples, and for instance, Alexeyev constructed such counterexample which, when we have just function which is continuously differentiable, but not C11, and then the result fails. Okay, so let's look at some simple examples. The first are quadratic maps. So let's deal with finite dimensional space, Euclidean space, and so we have m quadratic functions, scalar quadratic functions. So it is the map. So the map F has these components which are quadratic. So we have a map from n-dimensional space to m-dimensional space. This is such quadratic map. Okay. So the only assumption in this case which we need is that these linear parts of our functions are linearly independent. So A, R, I are linearly independent, we assume. Then it can be checked that all conditions of theorem are satisfied, and then we have that if we consider a small ball centered in the origin of our space, and I remind that the norm we deal with here is Euclidean norm, then under assumption, so we can estimate precisely what is the radius, critical radius of this ball. it is given by this inequality where L is this quantity and nu is the least singular value of the smallest singular value of a matrix which has columns, these linear parts of this map. So if epsilon is less than this constant, then the image of a ball under this quadratic map is convex. And it can be seen on some particular example when two-dimensional, when we have two-dimensional quadratic mapping, so it's from R2 to R2. The components are given by these formulas, so the simplest things. And the theorem guarantees that if epsilon is less than this constant, then images are convex. And if you calculate these images, they look like this. So these are images of disks, epsilon disks for different epsilon. And so you see when epsilon is small, it's convex, and then it loses convexity for larger epsilons. Okay, so this is the general result. And now let's look how it works in different fields. So I'll start with the simplest situation. It is just a linear algebra. So it's so-called pseudospectrum. So what is pseudospectrum? Let's take n by n so square real matrix. Well, it has some n eigenvalues. Now let's take perturbations of this nominal matrix A. And perturbations are bounded in Frobenius norm. So the Frobenius norm of these perturbations are less than epsilon. So the Frobenius norm is just square root of sum of the squares of entries of the matrix. So we take all eigenvalues of these perturbed matrices. So then each eigenvalue of our original matrix is diffuses to some cloud, and this is a pseudospectrum. Okay, so under just one assumption that all eigenvalues of our matrix are distant, so all of them are simple eigenvalues, we can prove by using this general result that our pseudospectrum consists of n convex set on a complex plane. So of course, if we have a real eigenvalue, then and it's simple eigenvalue, then for perturbed matrices, it remains real. It cannot become complex. So for real eigenvalues, these sets are just intervals. It's not a problem. But for complex eigenvalues, we have some such clouds around each eigenvalue. So the statement is that they are convex sets. And it's interesting that the result is not true for multiple eigenvalues. Okay, just a couple of words. So how we apply the theorem. So our space X is a space of real n by n times n matrices equipped with scalar product, which is equal to trace of A transpose times B. And then it's a Hilbert space, so, and the norm which corresponds to this scalar product is exactly the Frobenius norm. And we have this mapping from this space to complex plane, which can be understood as R2. And so we can check the conditions of our theorem. So these regularity conditions is ensured if eigenvalues are simple. So that's all. And for instance, if we have multiple eigenvalues, so if, for instance, something like this, so we have, say, an eigenvalue of multiplicity 4. Then for perturbed matrices, for small perturbations, it looks like something like this in many cases. So we have the image is some set like this one. So it's non-convex, even for small epsilon. So this assumption is essential. And about Frobenius norm, well, actually it's not quite clear how probably in some other norms it is these sets are also convex, but definitely for some norms they are not. For instance, a norm which corresponds to interval matrices, say a norm of matrix which is equal to maximum of absolute value of entries of a matrix. Then the set is these sets are non-convex. Okay, so it was application to linear algebra. So now let's look at optimization. So here is a standard mathematical programming problem. We have its minimization of some objective function subject to inequality and equality constraints. So it's well known that if the problem is convex, that is the function f0 and functions fi for I from 1 to L, if they are convex, and if other functions which correspond to equality constraints are linear, then it's a convex optimization problem, and we have very nice duality theory and so on. But now we don't assume convexity. All these functions are non-convex. The only assumption they are smooth enough. Okay, but we consider not the original problem. We consider this problem with one extra constraint. The constraint is the solution should belong to some ball centered in a point A. And the radius of this ball is some epsilon. Okay. So we construct the Lagrange function as usual, and we make the critical assumption. The assumption is that and the gradients of all functions, including objective functions, are linear independent in the point A, which is the center of the ball. So what does it mean, this assumption? For instance, if we have just equality constraints, this just means that the point A is not a solution. Well, actually, it's not a solution of a regional problem without this extra constraint. It's also not satisfies Lagrange multiplier rule. Otherwise, if we add this extra constraint, nothing changes. So if it is a critical point in the original problem, this constraint doesn't play any role. So we assume it is not the case. So it is the assumption that all gradients are linearly independent. And what is surprising that under these assumptions, we have the standard assertion, which is exactly duality theorem for convex programming. And again, I insist that it is not a convex problem. All functions were non-convex, but still we have this duality result, exactly the same as in convex case. But not exactly, actually. We have this inequality just for points in a ball centered in the point A. And it's under the assumption that the radius of this ball, which is the extra constraint, is small enough. Okay, we can say more, as you maybe, well, probably you had no time to see that actually the Lagrange function here includes all our functions, constraints and objective functions in a similar way, but standard Lagrange function is slightly different. It is when we take y0 equal to 1. And so under some regularity conditions, it's so-called Slater-like condition, we can prove that the result is true for with this extension. And again, how the result is proved? How we can apply the theorem. First of all, we take this set F, which is the image of our ball. And then our initial problem, our minimization problem, can be rewritten in the form of minimization of the first coordinate of a vector subject to constraint that our vector belongs to this set F capital and non-negativity of some other components of the vector. So if this F capital is a convex set, then we have a convex problem in this image space. And well, then all duality theory works and we can establish our result. And it is really convex due to this convexity principle, which I mentioned at the beginning. Okay. So it was about duality for such non-convex problems. And now about numerical methods, just a few words about numerical methods. Let's consider the simplest problem, which probably the simplest problem which can be the simplest unconstrained minimization problem. So we are looking for minimum of scalar function f of x subject to one constraint, that x belongs to the ball. And the only assumption is that the derivative at the point A is not vanishing. It's not zero. Then we can construct such an iterative method for solving this problem. So you see, it is iterative, but it has not a standard structure of iterative methods when a new iteration is got from previous iteration, and we make some step from previous iteration. Here we return back to the point A all the time and make steps only from this point A. And the step size in this case is exactly epsilon. So we are we start somewhere, we calculate the gradient here and make a step from point A. We go parallel in parallel direction to this gradient, and we go to the boundary of this set and repeat. So the result is that for this particular case, this method converges to a solution, and it globally converges. Well, actually, that's some local problem on this small ball, but nevertheless, we don't assume convexity of our objective function, but nevertheless, we have global convergence, and it is true if epsilon is small enough. And what does it mean, small enough? It depends on the value of gradient of this at the center of our ball, and Lipschitz constant for derivative of function f. Okay, and we can also estimate the rate of convergence. Well, now I jump again, and now we proceed to control problems. So let's consider the control problem in this form. Well, it's more or less standard. So we assume some fixed interval, time interval. We assume that the initial condition is given, and the only constraint for controls is this L2 bounded. That is the L2 norm of our control is bounded by some epsilon. So if we understand control as some, so it in some sense it's just a power of our control. So it's low power control, and then we can define a reachable set for such systems. That is, when control runs through all admissible controls given by this inequality, all trajectories at the time t capital, well, they construct some ball, some set, which is we denote S, and which is a reachable set. So, okay, now some assumptions. Of course, if this system was linear in X and U, there was no problem, then this reachable set was convex for any epsilon, and it is trivial, but we don't assume this system to be linear. What we do assume that a linearized system is controllable. So, well, controllable means that for this linearized system, any point is reachable for some control without constraints on control. Any point in the set is reachable from 0 if we apply arbitrary controls. So it's the controllability property. And then more or less, well, we have also some technical assumptions on smoothness of right-hand side of our system. It's not a problem. But again, the result is that if epsilon is small enough, then the reachable set is convex. So the system is nonlinear, but the reachable set is convex. So all here these points so here is this reachable set. And again, we apply the same result. So in this case, our initial space is L2, space of controls, equipped with L2 norm, and the space Y is n-dimensional space of the points xt, and all assumptions of our theorem are fulfilled. Okay, so if the set is convex, then we can validate many results in optimal control. For instance, if we have some optimal control problem that is, well, of this form, minimization of some terminal term, and if this function is convex, well, for instance, linear, then we can say we can actually, in this case, it can be converted into finite dimensional optimization problems for these images, and for convex optimization problems, we know that necessary and sufficient conditions are the same. And so we can, returning to our initial problem, we can claim that maximum principle for this problem is not only necessary but also sufficient condition of optimality. Then we can construct numerical methods for the problem. Actually, it's exactly the method which I have written, minimization subject to one inequality constraint, one minimization on the ball. We have this problem here, so well we can apply that result, and we have global convergence of the method for this case. And well, to conclude about control, we can treat also discrete time version of the program when we have not a differential equation but difference equations, and we also have the constraint for control of this form. Then again we can apply our convexity principle for this case, and we can state that for epsilon small enough, the reachable set is convex, and so on and so on. So for this particular class of optimal control problems, everything is very nice. It's the same as for linear systems. Okay, so just to conclude, I would say that it looks like a helpful tool for treating some various problems in optimization, control, linear algebra, and so on. There are still some open questions, and probably there are some extensions of the results which I presented. But it's for future work. And some results can be found in these publications. And I have some reprints of them, and can provide them to those who are interested. Okay, that's all. Thank you. Or condition on
F, capital F.
On the map to get convexity of the ball.
So
That'd be probably the second slide.
okay, okay. And so the theorem itself is here. Okay. Okay. He will.
I have a question concerning your local optimality, the second application
Yes.
to math programming. How do you compare the regularity conditions you need with respect to standard Lancaster problem conditions?
Well, it's a little bit different. It is specific. I can show you. It's well, it's of the same sort, but a little bit different.
Do any of them imply the other?
No, they are specific. We need a little bit more than in Mangasarian form of its regularity condition.
Yes, Bernard.
Last question. What's the tool you use to prove that the system of the nonlinear equation have a solution in the good region?
Yes.
What's the tool?
Graves theorem, well, actually it is proved by Newton method. Actually, the technique is to prove of proving is, but what is the problem here? That Newton method in its original form cannot be applied because it's the mapping from one space to another, which is, well, really the dimension of this space is smaller. So there are many solutions of linear equation at each step of Newton method. So it should be.
You cannot use Cantorovic's.
No, we cannot. Cantorovich theorem is, well, when we are, the map is in the same space, and here it's different. And it's very important here that we always apply, for instance, well, in optimal control, it was from infinite dimensional space, L2, to Rn, and so on. So, or in linear algebra, it was from Rn square to R2. So these are really different spaces, X and Y.